Can you imagine this Earth on which we humans have been born? This Earth which is home to innumerable species of living beings. This very Earth was a ball of boiling lava 4 billion years ago, a ball with no sign of life. This begs the obvious question, how did this ball of lava transform into the Earth we live in today? Where did water come from? How was the moon formed? These are all connected to the birth of our sun and solar system. In this video, let's understand these in depth. About 4.6 billion years ago, that is 4,600,000,000 years ago, our solar system did not exist. Instead, there was only darkness, deep, quiet, and empty space. In this space was a cloud full of dust and gas. This cloud is now known as the solar nebula. In Hindi, it is called Niharika. It contained various gases. Of them, hydrogen and helium were the most abundant. This cloud was peacefully traveling through the darkness of space for millions of years. Then suddenly, one day, there was a big explosion. And no, I don't mean the Big Bang, I am talking about the supernova. This explosion wasn't caused inside the cloud, it took place somewhere close to it. A dying star exploded near it. This kind of explosion is called a supernova, and it often happens to those stars which reach the end of their life. The shock waves of this explosion reached our solar nebula and caused gravitational instability. In some areas of this cloud, the gas and dust began compressing. Gradually, this entire nebula started collapsing inward, and the gas and dust started revolving around it. The nebula looked like a rotating disk at this point. This flat, rotating disk is called the Proto-Planetary disk. Proto means before. The disk that existed before the planets were formed. As shown in the animation on the screen, this was what the disk looked like. Since this disk was flat, this helps us understand why our solar system is flat. I talked about this in the Voyager video. When the planets of our solar system orbit around the sun, they are almost on the same plane. The orbits of the planets aren't significantly higher or lower than the others. Now, at the center of this protoplanetary disk, the pressure and temperature kept on increasing, and it gave birth to a protostar. Protostar means the same thing, basically. The thing which existed before the star was formed. Gradually, the contents of the nebula were pulled towards the center due to increasing temperature and pressure, and at one point in time, the center became so concentrated that nuclear fusion reactions started. Hydrogen's fusion reaction. It takes place at around 15 million degrees Celsius. In this reaction, hydrogen turns into helium. Because of this fusion reaction, our sun was born. This reaction is still taking place on the sun and is the source of sunshine, heat, and light on Earth. The details of the actual reaction are quite complex, but broadly speaking, hydrogen is being converted into helium. Back then, 4.6 billion years ago, most of the gas and dust in our solar nebula was converging into the sun. This is why even today, the sun makes up about 99.8% of the total mass of our solar system, and the remaining 0.2% didn't go unused. That 0.2% accounts for 8 planets, hundreds of moons, thousands of comets, and millions of asteroids in our solar system. But the question is, how did these planets start forming? That's so interesting. Small dust particles in the rotating protoplanetary disk started colliding with and sticking to each other. This happened due to static or chemical bonding forces, and initially, they formed into small clusters. Millions of years later, the clusters started getting bigger when more dust particles collided with them. Gradually, some of them got so big that their diameter ranged from 1,000 meters to a few kilometers. These bodies are called planetesimals, a tiny version of planets. When gravity pulled these planetesimals together and their mass or size became as big as our moons, they were called protoplanets. The process of these dust particles accumulating together is known as accretion. Look at how accretion is defined in astronomy: the coming together and cohesion of matter under the influence of gravitation to form larger bodies. The accumulation of materials leads to the formation of larger bodies. This process of accretion was presented to the world by a Soviet Union astronomer, Viktor Safronov, in 1969. But back then, no one took him seriously. It was only in 1984 that Safronov's work was being studied, and his ideas were being adopted by the scientific community. Today, scientists have observed this process of accretion all over the universe through powerful telescopes. Astronomers have seen this happening in other solar nebulae, where dust particles accumulate quickly, and in just a few thousand years, they scale up to around 1 centimeter. Since this was observed in different stages, scientists can now confidently say that for millions of years, these small particles keep on growing and eventually become planets. Another proof of this process can be seen in meteorites. When scientists study the meteors that fall on the Earth to check their chemical composition, one of the things that have been found repeatedly is chondrules. These are small pieces of dust and rocks from the time before the formation of the planets. They contain radioactive elements like uranium and hafnium, which helps scientists find out the age of these bodies. By the way, another interesting fact is that the uranium found on our Earth is older than our solar system. It is considered to be 6 billion years old. This means that it was formed in some supernova. By collecting data from these measurements, scientists can come up with simulations of the collisions of dust and planetesimals. And these simulations help us estimate that it would have taken tens of millions of years for the protoplanets to form. Now, talking about our Earth, these small protoplanets and planetesimals often collided with each other. These weren't small bumps. They produced a lot of energy. These generated so much heat that it melted rocks, giving rise to seas of lava. As these protoplanets collided with each other, they became bigger. Because of gravity, over time, they started becoming spherical in shape. And after numerous such collisions, our Earth was born. Over millions of years, gravity pulls these rocks together to form the Earth, one of at least 100 planets circling the Sun. During this period of constant collisions, small protoplanets or planetesimals would collide with our Earth frequently. This period is known as the Hadean Eon. The word eon means an indefinitely long time, and the name Hadean is derived from the Greek god of the underworld, Hades. I guess you've already understood why they chose this name. Back then, Earth was just like how hell is described. This was the time between 4.6 billion years ago to 4 billion years ago. Some objects that collided with the Earth during this period were as big as 100 or even 200 kilometers in diameter. Any rocks that existed on the Earth at that time would melt and turn into lava, being compressed repeatedly. But now comes the most amazing part. This hellish eon was the reason we have water on Earth. Some comets and asteroids that collided with Earth contained high concentrations of water in them. You might ask how those asteroids and comets got water. Friends, that was because of the solar nebula. The cloud of dust I mentioned earlier in the video contained ice crystals too. Even our Earth had some water. When the minerals trapped inside the microscopic crystals from the Eon period were analyzed, it was discovered that liquid water was present on the Earth as well. But the increasing water reserves on Earth was caused by the colliding asteroids and comets. Simultaneously, there was another process underway. During these collisions with the Earth, the water would become steam and go into the air, and after some time, it would come down as rain. By the end of this Hadean Eon, our Earth had become a homogeneous ball. There was magma all around. The Earth had become almost like a uniform layer of lava, held together by gravity. This led us to differentiation. You might be wondering again about how can we know for sure that these events did happen back then. Friends, the findings are supported by numerous techniques. One of them is radiometric dating of rocks, studying billions of years old minerals to check their composition. Another technique is comparative planetology, looking at the composition of other planets to understand what they looked like in recent history and how they developed. And the third is running computer simulations. The gases and elements present during then are taken as inputs for the program. The model runs based on this data. Scientists then monitor the model's behavior. Today we all know about Earth's three main layers, the crust, mantle, and core. By the end of the Hadean Eon, Earth's crust had already started to form, but the separation of these three layers happened during the next period, the Archean Eon. The word Archean comes from the Greek word arche, which means beginning. So from this period, basically, Earth began to take shape. This period lasted from 4 billion years ago to 2.5 billion years ago. During this period, the ball of lava, which was our Earth, there were different elements in it. The heavy elements like iron and nickel, because they were denser than the other elements, gradually started flowing into the magma and started accumulating at its center. Just like how water makes its way through the sand. The simple reason behind this was the force of gravitation. The heavier elements, iron and nickel, kept being pulled towards the center, and the lighter elements started flowing upwards towards the surface, like silicon, oxygen, aluminum, sodium, calcium, potassium. The flow of the various elements towards the center, or the surface, kept speeding up with time, and slowly, at the center of the Earth, the core began to take shape, when iron and nickel started fusing together. We know that Earth's core is its hottest component. The temperature reaches up to 6,000 degrees Celsius. Usually iron would melt at this temperature, but the pressure at Earth's center is so high that iron doesn't melt at this temperature. Rather, iron and nickel are present in the Earth's core in its solid forms. It is the same today. And the reason behind this high temperature is not only the high pressure and gravitational force. Another reason is the constant radioactive decay in the mantle layer. Elements like uranium, thorium, and potassium lie in the mantle layer. They are undergoing constant radioactive decay. This is a major source of heat for Earth. Mantle is the thickest layer. It is more than 3,000 kilometers thick. Today, this layer is solid. But back then, this layer was not solid. It was full of magma. When the lighter elements were flowing upwards, they cooled at the surface, and so the topmost layer, the crust, was formed. Oxygen was the most abundant element in this crust. 46% of crust's mass was made of oxygen. If we go into the details of these elements, we can have a lengthy discussion. The different types of rocks found on the crust today, granite, basalt, metamorphic rocks found in the deep layers of the crust, like marble or slate. These present a clear-cut transition as you move outwards, from the mantle towards the crust. Because rocks like marble and slate form due to extremely high pressure and temperature. That's why they are found only in the deep layers of the crust, and if more heat and pressure is applied on them, they turn back into magma again. Apart from this, there are sedimentary rocks in the upper layers, such as sandstone. These rocks were in a constant cycle of formation and breaking apart due to weathering, because they were exposed to sunlight, air, water, and snow. Coal is also considered a sedimentary rock. It is a type of sedimentary rock that has gone through both chemical and physical reactions. So, broadly speaking, this differentiation process continued for millions of years, during which the layers of our Earth were formed. Students are often taught only about the layers crust, mantle, and core, but actually, there can be many more differentiations in the layers. If you study geology in detail, you will find that Earth is differentiated into not 3 but 5 layers based on their physical properties. These layers are the lithosphere, asthenosphere, mesospheric mantle, outer core, and inner core. Lithosphere is the topmost layer. It is divided into 2 parts, oceanic and continental, the crust under the oceans and the crust under the continents. They are significantly different. The crust under the oceans is quite thinner. There, the average thickness is around 100 kilometers, but the crust under the continents can be up to 280 kilometers thick. Here we come to the tectonic plates, because this isn't a continuous layer. In fact, it is made up of many parts. The areas where the boundaries of these plates meet give rise to volcanoes. When they rub against each other, it causes earthquakes. The layer under it, the asthenosphere, isn't rigid. It moves constantly. It acts like a lubricant. The word astheno means weak in Greek. And this layer, unlike the lithosphere, is continuous. It doesn't have parts or pieces, and its average thickness is about 140 kilometers. Below this, in the outer parts of the lower mantle, you can see a transition zone, where the rocks become denser. Some examples of such rocks are olivine, peridotite, and ringwoodite. These high-pressure minerals form inside the mantle, and as you can see, they look beautiful. Now, if these minerals are found inside the mantle, how did we take them out of the mantle and see them? Actually, we did not take them out. Nature, our Earth, brings them out. At times when there are volcanic eruptions, the magma that erupts from the volcano and brings with it these high-pressure minerals from the mantle. Or sometimes when a meteorite falls to the Earth, they collide at such a speed that this pressure is enough to create such minerals. Moving inwards, we get to the core. In the outer core layer, iron keeps on churning due to the heat. This generates electrical currents. Since iron is a good conductor of electricity, these electric currents then form a magnetic field. This magnetic field is one of the primary reasons why Earth could sustain life. It is this magnetic field that provides protection against the harmful charged particles emitted by the sun. It protects us against solar winds and helps hold the atmosphere together. The biggest difference between the outer and inner core layers is that the outer core is in liquid state and the inner core is solid. And interestingly, as the liquid in the outer core cools down, it is solidifying. And this is why the layer of the inner core increases by about 1 millimeter every year. Now, another question in this story is, how was the moon formed? The Earth was formed, but how did the Earth get its moon? Friends, the answer lies in the Hadean Eon. Scientists considered many theories about how and why do we have the moon. One of them was the capture theory, that it was a planetary object which came close to the Earth and was captured by Earth's gravitational force. This is known as the capture theory. Another theory was the co-formation theory, that the moon and the Earth were formed at the same time. When Earth was being formed, bits and pieces of dust particles were combining together. The moon was forming similarly. Yet another theory is the fission theory. A part of Earth broke apart and became the moon. But do you know what? None of these theories were true. Today, most scientists believe that another planet collided with Earth, and this collision led to the formation of the moon. This theory is known as the giant impact hypothesis. According to this, about 4.5 billion years ago, while Earth was forming, there was another protoplanet. That's been named Theia. It was about the size of Mars. About 100 million years after the solar system was formed, this planet collided with Earth. At this point, Earth was only a ball of lava, and so was this planet. So what happens with this collision is that the cores of both the planets fuse into one. In the meantime, a large chunk breaks apart, which later becomes the moon. 30% of Earth's total mass is due to its iron-rich core, but in Moon's case, it makes up only 1.6% to 1.8%. This means that most of the metals on this other protoplanet remained on Earth and have become a part of our planet, and the Moon came from the debris of this collision. Are you wondering how we can be so sure of this? Actually, when NASA sent the Apollo missions to the Moon for the first time, they brought back soil from the Moon. The samples of basaltic rocks found in the Moon's mantle were very similar to the basaltic rocks found on Earth. The oxygen isotopes and other elements found in the Moon's rocks were quite similar to those found in rocks on Earth. So, from this perspective of the three rejected theories, the fission theory was the closest to the truth. The Moon was actually a part of the Earth, but it wasn't like the Earth broke apart on its own and the Moon fell off. A chunk of Earth broke apart only when another planet collided with it horrifically. On the screen you can see a simulation of this event created by NASA's supercomputer. But do you know what's amazing? Without this collision we would not be alive today, because this collision made a huge impact on Earth's axis. This caused the 23.5-degree rotational tilt. Without this rotational tilt, we wouldn't have seen seasons change from summers to winters and back to summers. The climatic variations would have been so severe that it would have been extremely difficult to adapt to life. Secondly, without the Moon, there would be no oceanic tides. These variations, known as low tides and high tides, helped living organisms move from the oceans to land. Coming back to the Earth and the Archean Eon, there were many other developments that gave life a chance to begin. After the separation of the three main layers, things started being stable. There was a lot of volcanic activity. Volcanoes erupted. This caused a large amount of gases like water vapor, carbon dioxide, methane, and ammonia to be emitted into the air. This is actually a toxic mixture of gases because it direly lacks oxygen, but with time, as the Earth gradually became colder, water vapor started to condense. This condensed water vapor started to rain down on the Earth, and after millions of years, we have these huge oceans on Earth's surface. I have already told you the other reason behind the formation of oceans in a previous video. The impact of the constant collisions of asteroids and comets. This liquid water was present in large quantities. It played a crucial role in life on Earth. It absorbed most of the carbon dioxide and heat from our atmosphere. Because of this, on Earth's surface, the temperatures could become pleasant enough and the oxygen levels started rising. Do you know what's amazing, friends? Even today, the carbon emissions, the carbon dioxide released by human activities, most of the carbon emissions are actually absorbed by our oceans. Many people believe that forests and trees contribute the most, but it is not so. The oceans are the ones to clean up, but unfortunately the ocean's capacity is gradually getting towards the end. This is an interesting topic and I can make a separate video on it if you want me to. Comment below if you do. For now, I would like to end this video at this point. The events I talked about in this video were the preconditions. Had things not been so, perhaps life wouldn't have gotten the chance to propagate. The Sun being at just the right distance from Earth, neither too far nor too close. Earth size being just the right proportion. Don't forget to subscribe to Technosphere for more fascinating videos about our planet and beyond.